Through our previous videos, we were building our basic concepts of physics in semiconductors. These concepts can be used to understand the working of various devices which uses semiconductors. The primary constituent of the current in a semiconductor, as you all know, are electrons and holes. More specifically, it is the excess carriers which is generated that contribute towards the current in semiconductors. In this video, we shall discuss about the excess carrier generation and recombination in detail. This will help us understand the current in semiconductor, which in turn will help us to understand the working of various devices which uses semiconductor. We had stopped in our previous video with a mathematical representation being derived, and the mathematical representation goes like this: N0 P0 is equal to Ni square, where N0 is the number of electrons, P0 is the number of holes in a general semiconductor, and which is the product of these two is equal to the square of number of electrons in an intrinsic semiconductor. This mathematical expression is universally known as the law of mass action. In other words, the law of mass action states that the product of number of electrons in the conduction band and the number of holes in the valence band is constant at a fixed temperature and is independent of amount of donor and acceptor impurities added. If we rewrite the same equation of law of mass action for n-type, we just make a slight change as n suffix n into p suffix n is equal to Ni square. N suffix n means the number of electrons and p suffix n is the number of holes for the n-type semiconductor. And we know for n-type semiconductor, electrons are the majority carriers. Similarly, for p-type semiconductor, the law of mass action is rewritten as n suffix p into p suffix p is equal to Ni square, where Np is the number of electrons and Pp is the number of holes in case of the p-type. Here what we have to keep in mind is that the majority carriers are the holes and the electrons are minority carriers in this type of semiconductor or the p-type semiconductor. Just a look back on the energy band diagram which we had seen in our previous video. As you see, the Fermi level is at the exact center of the energy band gap, or is same as the intrinsic energy level EI for intrinsic semiconductor. And we also know in case of intrinsic semiconductor, number of electrons will be equal to the number of holes available. In case of n-type, the Fermi level is closer to the conduction band. Here the number of electrons is more than the number of holes. Electrons are in the conduction band and holes are in the valence band. N is greater than P. For p-type semiconductors, number of electrons in conduction band is less than number of holes in the valence band. P is greater than N here. And also in the diagram, it's clear that the Fermi level is more closer to the valence band. In today's discussion, we will be concentrating on the excess carriers. And while we discuss about excess carriers, we do it in two segments. The first segment will describe about the generation of excess carriers. Generation describes processes by which electrons gain energy and move from the valence band to the conduction band, producing two mobile carriers. Why two mobile carriers? The electron which is gaining energy moves to the conduction band, leaving behind a hole in the valence band. So there is an electron in the conduction band and hole in the valence band. So we are getting two mobile carriers. The next segment is the recombination, which describes the process by which a conduction band electron loses energy and reoccupies the energy state of an electron hole in the valence band. Or in other words, the electron which was earlier energized to the conduction band loses that energy and comes back to the valence band, so as to fill the available hole in the valence band. Most semiconductor devices operate by the creation of charge carriers. This creation of charge carriers and the recombination makes the semiconductors eligible to be controlled conductivity. And that controlling of the conductivity is the speciality of the semiconductor that we make use in the various devices which use a semiconductor. The excess carrier dominates the conduction process. That is why we are discussing in detail about excess carriers, and we shall see how the excess carriers, or what are the different ways the excess carriers can be generated. One methodology of generation is by light absorption. Carrier generation due to light absorption occurs if the photon energy is large enough to help the electron from the valence band to move on to the conduction band, empty states in the conduction band, thereby generating one electron hole pair. Please keep in your mind, this is a new terminology or new phrase that you have to keep in your mind, which is the electron hole pair. Whenever an electron is energized or attains energy to escape from valence band to reach conduction band, it leaves behind a hole in the valence band. So always, if there is a free electron, there will be a hole. So they makes a pair. Whenever an electron is made, a hole is also made. That is why it is called as electron hole pair. And in case of generation due to light absorption, the photon energy is the energy which helps the electron to escape from the valence band to the conduction band. The only criteria this photon energy should maintain is that the photon energy needs to be at least equal to the band gap energy to satisfy this condition. In other words, if only the photon energy is capable of taking the electron from the valence band to the conduction band, this type of generation is possible. Next type of generation is by the application of electric field. This can be termed as the generation due to impact ionization. Generation due to impact ionization is caused by an electron with an energy which is much larger than the conduction band edge. This excess energy is given off to generate an electron-hole pair through a band-to-band transition. In other words, if a particular electron in the edge of the conduction band is having more energy than required, it gives that energy to a different electron, which in turns get energized, and that energy will help this new electron to escape from valence band to the conduction band. Next mode of generation of excess carrier is due to high energy beam, or generation due to high energy beam. The carrier generation due to a high energy beam consists of charged particles which is having available energy much larger than the band gap energy, can be used to excite the electrons from valence band to the conduction band. This type of particles will transfer its energy to the electrons in the valence band, which escapes to the conduction band, and this particle will lose its energy and stops there. So we had seen three types of possibility of generation to the generation of electrons from valence band to move to the conduction band. One is generation due to the photons of light energy. Next one is the electric field, due to electric field by impact ionization. And another possibility is using high energy beam. Now we shall see about the recombination. Recombination of electrons and holes is a process by which both carriers annihilate each other. Means the electrons occupy through one or multiple steps the empty state associated with a hole. After recombination, it is evident that both the carriers disappear. As in the case of generation, we said whenever a hole is generated or whenever an electron is generated, correspondingly a hole is generated, and that is why it is called an electron-hole pair. Similarly, in case of recombination, whenever an electron comes and occupy the space of hole, both electrons and holes disappears. And this process is known as the recombination. There are different types of recombination or different ways of recombination in case of semiconductors, different semiconductors. One is the direct recombination. We have already seen direct semiconductors and indirect semiconductors, where the direct semiconductor releases light energy whenever it recombines. In direct recombination, an excess population of electrons and holes decay by electrons falling from the conduction band to the empty state in the valence band directly. Energy lost. Whenever an electron falls back into the valence band, there will be release of energy. In this case, the release of energy is given up as photons or light energy. Another aspect of direct recombination is it occurs spontaneously. That is, the probability that an electron and a hole will recombine is constant in time. In this case of direct recombination, the rate of decay of electrons at any time t is proportional to the number of available electrons at that time t and number of holes. This with some constant of proportionality for recombination, which is denoted by alpha r. Or in other words, the net rate of change in conduction band electron. What do you mean by change in the conduction band electron? Some electrons are coming back and falling into the valence band and recombining with the available holes. That is of the number change in the conduction band. So the net rate of change in the conduction band electron concentration is the thermal generation rate alpha r Ni square minus the recombination rate. So from the existing number of electrons, this gets reduced by recombination. It is mathematically represented by d by dt of Nt, which is the net rate of change in the electrons in the conduction band, is equal to alpha r Ni square, which gives the thermal generation rate, the rate at which the electrons are being generated, minus the rate at which the electrons decay, which is alpha r into n of t p of t. N of t means electrons at the time t. P of t means the available holes at the time t. Another type of recombination is the indirect recombination. We had seen examples for indirect semiconductors. Silicon and germanium falls under this category. In case of such semiconductors, recombination is happening in an indirect fashion. It is also known as trapping. There is a new level called recombination level for this indirect recombination. Earlier, we had introduced a level where the probability of finding electrons was 50%. That level was known as the Fermi level. Now we are introducing another level which is called by the name recombination level, which plays an important role in case of the indirect recombination. Normally, this level, recombination level, is below the Fermi level. And because it is below the Fermi level, this level will be occupied by the electrons at normal situation or at normal condition. Whenever an electron falls back from the conduction band, it comes to this level first and it occupies a vacant space here. How did a vacant space occur in this recombination level? One of the electron at this level had escaped to the valence band to fill the hole at the valence band. So, contrary to the direct recombination, in case of indirect recombination, electron from the conduction band will not directly move to the valence band hole, but it will move to a different level known as a recombination level, and from recombination level it moves to the valence band hole. That is why it is known as the indirect recombination. A recombination level ER, which is below EF at equilibrium, is being used in case of the indirect recombination. Another type of recombination is known as the Auger recombination. Here, this is a non-radiative process. Earlier recombinations, the direct and indirect recombination were radiative process, because in case of direct recombination, light energy was radiating out. In case of indirect recombination, heat was dissipated. In case of Auger recombination, which is a non-radiative process, here direct Auger recombination occurs when an electron and a hole recombine. But instead of producing light or heat, the extra energy, the excess energy which is being released will be given to an electron already available in the conduction band. So it will get more energy and it will move to higher level in the conduction band. Similarly, in case of valence band, holes will be pushed deeper. This happens because during recombination, in a band-to-band transition, energy is given off to another electron or hole. It is not released as light energy or heat energy, but given to the neighboring electrons or holes. Whenever an energy in a conduction band or electron in a conduction band gets more energy, it moves to higher level in the conduction band. Same in the case of holes, if it gets more energy, it moves deeper into the valence band. So this is one type of, or another type of recombination, Auger recombination. There are other variations of recombinations, one of which is the surface recombination. It is a trap assisted recombination, but at the surface level of the semiconductor. This occurs when traps at or near the surface or interface of the semiconductor form due to dangling bonds caused by the sudden discontinuation of semiconductor crystal. Another recombination is the Langevin recombination. This is applicable for free carriers in low mobility systems. The model is often used for disordered systems such as organic materials. So we have seen various types of recombinations, out of which the main types are the direct recombination, indirect recombination, and Auger recombination. With that, we have seen how the excess carriers are being generated and how they are recombined back. Now, because of these excess carriers, we need to make change in the Fermi level. Fermi level, as I had mentioned earlier, is a level which we had introduced where the probability of finding electrons is 50%. And we had introduced this Fermi level because it is often desirable to refer to the steady state electron and hole concentration in terms of Fermi levels for our analysis of number of electrons which contributes to the current in a semiconductor. But this Fermi level which we had introduced earlier is meaningful only when no excess carriers are present, or at equilibrium without any excess carriers. Now, since there will be excess carriers, we need to introduce a Quasi Fermi level. In order to continue the same pattern of analysis, we are introducing two Quasi levels, Quasi Fermi levels, Fn and Fp. Fn for electrons and Fp for holes, two different levels, which will be helping us to use the same steady state concentration technique for analyzing the number of electrons and holes. So we will be rewriting, or we are rewriting, the number of electrons n is equal to ni e raised to, earlier it was EF minus EI by kT. In place of EF we are writing Fn, which is the Quasi Fermi level for electrons. Similarly, number of holes P is equal to ni e raised to EI minus EF by kT was our earlier equation. In place of EF we are substituting Fp, which is the Quasi Fermi level for holes. So now the number of holes P will be equal to ni e raised to EI minus Fp by kT. Now the question is where we are introducing these Quasi level. So earlier we had only one Fermi level for the entire semiconductor, but in order to adapt to the existence of excess carriers, we are having two Quasi Fermi levels now. One is Fn, which is for the electrons, which will be approximately equal to EF, and another Quasi Fermi level is Fp, which is for holes. So in place of one Fermi level, to adapt the excess carriers in the semiconductors, we are having two Quasi Fermi levels. We will be making use of this idea in our further discussion of current in semiconductors. So with this topic, we are coming to the end of the module 1 of our syllabus for the solid state devices in the Kerala Technological University. And in order to understand more about the topics, we shall have a tutorial session on the topics covered so far in the next segment. So we have discussed the key points which is mentioned in the syllabus of solid state devices of KTU, which is being also displayed in the screen now. So we have gone through various basic concepts of intrinsic and extrinsic semiconductors, effective mass, Fermi Dirac, the Fermi level concepts, equilibrium and steady state conditions, density of states, effective density of states, and what are the equilibrium concentration of electrons and holes, law of mass action, and at last the generation and recombination mechanisms of excess carriers. And due to excess carriers, we have introduced a new level called the Quasi Fermi levels. So hope these videos are helping you out to understand the basic topics of semiconductors described by the syllabus for solid state devices under Kerala Technological University. Thank you, and we will have a tutorial session to just revise through whatever we had discussed under module 1. Thank you.